if you recall, last time we talked of the common source amplifier configuration for an NMOS device without source resistor. Now we have the same configuration, but we have included the source resistance. Well, the idea of including the source resistance is to stabilize the Q point. Okay, so you can stabilize your IDQ and VDSQ owing to inclusion of RS in the circuit. The reason is that you see from one transistor to another transistor, your conduction parameter Kn is varying. Okay, now owing to this variation of Kn, even in the small signal parameter, you will see that since the transconductance gain Gm, which is for an NMOS device, is given as twice square root of IDQ multiplied by Kn. So from transistor to transistor in the circuit, same circuit configuration, same external circuit elements. From transistor to transistor, the transconductance gain is a function of the conduction parameter that depends on the transistor. Okay, that one depends on the conduction parameter of the transistor. So RS tends to stabilize the small signal transconductance gain and the voltage gain AV, which is also dependent on GM. You will see in the small signal model that is GMRD. So with RS, even if your conduction parameter Kn, if it varies like plus or minus 10%, the variation in GM, the transconductance gain, and the voltage gain is less than 2%. Okay, so RS is there to stabilize the Q point and also the voltage gain parameters of the MOSFET amplifier. So now our source resistor RS is now, it tends to stabilize the Q point against variation in the transistor parameters. So if, for example, the value of the conduction parameter varies from one transistor to another, the Q point will not vary much, as if the source resistor is included in the circuit. Okay, so this was not the case last time. We didn't have any source resistor over here, so that's the reason. But it comes the cost is that the disadvantage is that the source resistor tends to reduce the signal gain at the same time. But that problem can be eliminated if you have a bypass capacitor. If you connect a bypass capacitor and let's say the signal frequency is about 2 kilohertz, at least 2 kilohertz, or say, then this bypass capacitor will act as a short circuit. Okay, will eliminate this problem due to the RS, and your signal gain won't be affected by RS anymore in the AC circuit. So this circuit in figure 19. So we'll take one example to show how having a bypass capacitor with the source resistance in common source MOSFET amplifier configuration can eliminate the problem of reduced small signal gain. Now in the circuit of figure 19, and this is figure 19, okay, this is a common source circuit. It shows the source resistor and the positive and negative supply voltages. So you have plus and minus 5 volts. Okay, so the circuit in figure 19 is an example of the situation in which the body effect should be taken into account. Now, if you recall, the body effect occurs if you have a potential difference between the source terminal of the MOSFET and the body or the bulk. So if there is a non-zero source to bulk potential, then you might have an AC component VSB, which you have to model, which you have to include in the small signal model. You have to include a back transconductance gain, and that is eta GM, if you recall. So what happens is that if you recall in the previous lectures, we modeled this body effect by GMB VBS. Okay, and this, if VBS is 0 or VSB is 0, what happens is that your threshold voltage is VTNO, but owing to a non-zero source to bulk voltage, the threshold voltage is a function of, it depends on the source terminal and the body potential difference. If there is an AC component, okay, then you have to consider, you have to take the partial derivative with respect to ID VSB, because the threshold voltage is also varying with respect to VSB, non-zero VSB. Okay, so because you see over here, if you have to drive, for example, M1, then you have to connect a positive VDS or VD1, okay, supply like this. So you see that VD1 is the same terminal as VS2. So the source is not ground. The source is not at the same potential as the body is. It is true for M1, but for M2, the source is not at ground. So by ground, I mean it's not the same potential of the body. So VSB is non-zero. Okay. So that means in the expression of the current and VGS characteristics, VTN is also depending on VSB. And due to that, if there is an AC component, you have to consider the back gate transconductance, okay, which we discussed last time. To do so, you have this chain formulation of partial ID with VTN, and then you consider VTN with VSB. So you use the same expression to evaluate VTN with VSB, and then you evaluate the transconductance gain. Okay, so from here, this expression, you'll have partial VTN over partial VSB. Okay, from this from the above expression, current expression, you can take partial ID with respect to partial VTN, take the product, and then you will have the dependence of the current. Okay, now if you multiply these two quantities, this quantity multiplied by this quantity, then it is equal to partial ID by partial VSB. That is, you're taking the dependence of the current on the source and bulk potential difference. So that gives you this GMB, that's the back gate transconductance. And then we found this as eta, okay. GMB is eta and the GMB is minus GM. Combining these two gives GMB eta. So, sorry, this is GM eta. Okay, this is not GM. This GMB is the back conductance, again, this is GM eta. So you have to model this in the small signal model. But for the sake of, you see, the situation is very similar over here. I mean, the VS is possibly not 0. Okay, it won't be 0 because in the previous configuration, VS was 0, which means with the body as compared to the body is grounded. Okay, the bulk is grounded. The body of the MOSFET substrate is grounded. So VS is also at the same potential. That means your VSB is 0. Okay. But once you have a source resistor, VSB is non-zero. In this configuration, VSB is 0, but over here, VSB is non-zero. Okay, it's some quantity greater than 0. So that means you have to consider the body effect. Okay, so normally the substrate, which is not shown, would normally be connected to a -5-volt supply. So the body and the substrate terminal are not at the same potential. But however, for the as far as the analysis of the circuit is concerned, and if you recall, what we talked about was that RS was there to tend to stabilize the Q point, which in turn, since the Q point defines IDQ, so the transmittance gain is there is stability, and then in turn we have the stability in the voltage gain. Although the transistor conduction parameter might vary from one transistor to another transistor, but that was the original idea behind the source resistor. So to ease the analysis, in the following example that we are going to take, we are going to neglect this effect. Okay, so we are going to have just single voltage control source that would be due to the input voltage at the gate terminal. Okay, VSG or VGS, and multiply by the transconductance gain to give the output current or the drain current. Okay, as far as the body effect is concerned, we are going to neglect that, and we are going to assume that VSB is 0, so there's no current source due to this bulk to source potential difference, AC component of the bulk source component. Okay, right, now this is example 4.5 from the course text. So the objective is to determine the small signal voltage gain of a Pmos transistor circuit. The circuit is there in figure 28. So this is Pmos circuit, for example 4.5. Transistor parameters are given as, so you have the conduction parameter for Pmos MOSFET device is 0.8 milliamp volt square. Then threshold voltage is negative, okay, 0.5 volts. If you recall, the threshold voltage for NMOS device is positive because you apply a positive gate voltage. For PMOS device, you apply a negative gate voltage to create the space charge region or the inversion layer. And then the channel modulation parameter is 0. Okay, the quiescent current is given as 0.297 milliamps. Well, what does this mean is that the output resistance, if you recall, we evaluated, we derived this in fact in previous video lectures. You might want to have a look on that. So the output resistance is given as 1 over lambda IDQ. So for a finite IDQ, if lambda is 0, that means the output resistance of the MOSFET device is infinitely large. So you don't need to consider the output resistance, right? And in the small signal model, we don't have any R0 over here, right? So the small signal equivalent circuit is shown in figure 20b. It's easy. The first thing is that we assume that the capacitive reactance is small at the signal frequency. So ZC is 1 over 2 pi FC. So we are not going to consider any capacitive reactance in the circuit. We don't have any RC over here. So just with VI, you have to kill all the DC sources. Okay, so this is ground. Again, this is also ground. So we are neglecting the DC sources. We are grounding them, and then you have a parallel combination at the gate. So R1 comes in parallel to this is the gate terminal. So at the gate terminal, you have R1 parallel R2, and we assume that the input resistance of the MOSFET device is large, and we don't consider any other capacitances, okay, besides CC, for which even we are not considering any reactive component of the capacitive reactance at the signal frequency. We are not considering any gate capacitance, and we are not considering even, we assume that the input resistance of the MOSFET device over here is infinitely large, okay. So we just have R1 and R2 in parallel at the gate terminal, and then this is a Pmos device, so source is at the higher potential with respect to the drain. The output is being taken from the drain, so this is my drain and that's my output, okay. So with V out, I have this RD, okay, RD is over here, and so my transconductance Pmos current direction will be opposite to that of NMOS device. So the input is again VSG, as being the source being at higher potential than gate, and GM is the transconductance gain, given as, if you recall, GM for Pmos device is given as twice Kp, okay, under root Kp multiplied by VTP, IDQ, right? So it can be determined directly from the given data. I mean, you have to have the quiescent current of 0.297 milliamps, so you can plug this value over here in this expression, find the transconductance gain. So multiply by VSC, that's the input voltage, gives you the current, and this current flows in the drain terminal, out of the drain terminal. So the direction of the current for the Pmos device is it's into the source, okay, out of the drain. So again, the current direction is out of the drain, so GM VSG, and you can see that this V0 is nothing but GM VSG, that's my current, and it flows through the drain resistor RD. All right, so this is RD. So, but now we have a source resistor, which is not directly source terminal, since it's not directly connected to the signal ground. So it's not signal ground. It's between the signal ground and the source terminal. We have the resistor RS, so we have to connect a resistor, include a resistor RS over here. So that completes our model. The small signal model is there. So you see the quantities associated with this small signal model. The output voltage is given as V0 is equal to, that's also the drain voltage, VD, if I may write this as such. This is the drain voltage, VD, AC drain voltage, which is equal to plus GM VSG RD. So GM VSG is my current ID. This is my current ID. So basically this is ID RD. So well, that's the same expression over here. The GM VSG is this current which flows into the drain resistor RD over here. Okay, this is RD. And then the other thing is, if you apply the Kirchhoff voltage law, KVL equation, from the input around the gate source loop, we find that so you see VI is it appears across R1 and R2 in the AC equivalent circuit, but then it's also the summation. If you look at the circuit, VI, if you apply the KVL around this gate to source output loop. Then this is can be written as minus VSG, and the potential drop across, you have to include the potential drop across your source resistor RS. So the current is, again, looking at the current direction, this becomes minus GM VSG multiplied by RS. Okay, so that's my input voltage that is available, the signal voltage. Okay, now if you write this expression in terms of VSG, that can be written as VI minus VI divided by 1 plus GM RS. Okay, so that is my VSG. So this is the VSG voltage that is available, multiplied by the transconductance gain gives you the drain current. Okay, so okay, we have this expression over here. This is the KVL that you apply in the circuit over here. You include this VSG and the voltage drop across RS, add them up, and then you have this VSG in terms of the input signal voltage. That's given as minus VI over 1 plus GM RS. Okay, so for a non-zero transconductance gain, the input voltage will have VSG as a fraction of the input voltage. Okay, of course, because some of the voltage is being dropped at the source RS. Okay, which was not the case. When we didn't have this RS over here. So we're going to expect a reduced signal gain anyways. Okay, because of RS, we don't have VSG as VI. Okay, it's a fraction of VI. So that means if you plug this expression for the valuation of the voltage gain, if you substitute this expression VSG into the output voltage equation, you find the small signal voltage gain as so you have the input voltage. Okay, it's the same expression minus over here, and you know that the output is GM VSG. So just plug this over here. Okay, and you have the voltage. You can write this as V naught over VI. It's given as minus GM RD over 1 plus GM RS, and you see that your voltage gain has been reduced. Okay, and if you want to compare this with the last example we talked in part 41 of the lecture series, even if your Q point is not at the center, this is an example where the Q point was at the center of the DC load line, was minus 6.58, and even when if the Q point is not at the center, we had this as minus 5.2. I mean, the voltage swing was less, but still, this is not the including the source resistor has almost halved this, reduced the voltage gain by 50%. So that's one of the disadvantages, including RS. So we might want to, if we might want to improve this gain, we can do that by introducing a bypass capacitor in the circuit, which is going to short circuit the RS and then include the current source for biasing instead. So, but anyways, let's complete this example. So the small signal transconductance is given as twice under root K peak IDQ. So we just have the IDQ as 0.0297 milliamps. KP was given as 0.8. Okay, IDQ was 0.297. That's given. KP is also given. So just plug these values in this expression. So GM is there. Okay, everything is known. Okay, from the given data. So the comment is that the analysis of the Pmos transistor circuit is essentially the same as that of an NMOS transistor circuit. The voltage gain of the MOS transistor circuit that contains the source resistor is degraded compared to the circuit without the source resistor. So we have seen that this response, the voltage gain is degraded by 50%. However, the Q point tends to be stabilized. Okay, the discussion is as such that you see your KP was the nominal value was 0.8. So if you are going to reduce this by minus 10%, or you are going to increase this by plus 10%, well, what happens is that first of all, your transconductance parameter in terms of amps per volt, there's not much variation. Okay, then you consider the voltage gain. The variation is even less than 2%. So with a plus minus 10% variation in KP from one transistor to another transistor in the same configuration, if KP varies, okay, because GM, you see the direct connection with KP, it's under root KP multiplied by IDQ, okay, and even if KP varies twice. 10% variation of KP produces less than 1.8% variation in both the voltage gain and even it has a less small variation in the transmittance gain as well. But yeah, the variation in the voltage gain is smaller. All right, so it doesn't affect, including RS does degrades your voltage gain. Okay, it does degrade, reduces the voltage gain, but at the same time it tends to stabilize the voltage gain, even if there is a variation in conduction parameter Kp. Okay. All right, now how to solve this problem? How to make sure that we have a stable Q point, but we should get a voltage gain at least higher, or at least what we had previously obtained without the source resistor at 6.58. How to do that? Now there is another example in the course text 4.6. We're going to talk about it in a while. So the solution is to have a common source circuit with source capacitor for stabilizing the Q point, but having this in parallel with a bypass capacitor. Okay, so a source bypass capacitor is added to the common source circuit with a source resistor with the source resistor will minimize the loss in the small signal voltage gain while maintaining the Q point stability. So we have a current source over here, we have a bypass capacitor over here. In the circuit, it's again a common source configuration. The Q point stability can be further increased by replacing the source resistor with a constant current source. Okay. In actual IC MOSFET circuits, you might have an enhancement type NMOS device over here, which is modeling the RS resistor. But again, for current source, you have the NMOS transistors over here. For the purpose of analysis, we are considering these resistance, but even these resistances are being modeled by the NMOS devices. Similarly, this current biasing source is also based on NMOS device in CMOS IC circuits. So the idea is just to show that if you have a bypass capacitor with the source resistor replaced by a constant current source, well, you have the Q point stability, and it can be further increased by replacing the stability is also further increased by replacing the source resistor with a constant current source. So the resulting circuit is shown in 21, assuming the ideal signal source. If the signal frequency is sufficiently large, so the bypass capacitor acts as essentially as an AC short circuit, the source will be held at the signal ground. So this part, the source is going to be at the signal ground, and this is going to minimize the loss first of all. Then again, because we're not considering the source resistor, but this is going to stabilize the IQ, the IDQ, the drain current at the Q point will be stabilized, and also you will see that the voltage gain will improve. Okay, so this is example 4.6 that illustrates these ideas. Now the objective is to, for example, determine the small signal voltage gain of the circuit biased with a constant current source and incorporating a source bypass capacitor. So it's the same configuration we talked of over here in figure 21. This is NMOS common source circuit, the source bypass capacitor, right? So the transfer parameters are the threshold voltage given, the conduction parameters of the transistor is given as 1 milliamp volt square, and again the modulation channel width modulation parameter is 0. That means the output resistance, this implies the output resistance, which is 1 over lambda IDQ, and we know what IDQ is. IDQ is 0.5 milliamps, okay, so it's a non-zero drain source current. Okay, so this is IDQ is 0.5 milliamps, but lambda is 0. That means the output resistance is infinite. We're not going to consider this in the small signal model. Okay, now since the DC current is 0, okay, we don't assume any gate current inside of the NMOS device, IG0. So the DC voltage at the source terminal is given as VSS minus VGS. Okay, so this is actually that can be written as VG minus Vs, and you can see this, the configuration is as such. There is no DC biasing at the gate terminal. There's no DC biasing at the gate terminal, and there's no biasing resistor R1 and R2 like we had previously over here. Okay, yeah, we don't have any R1 R2 which acts as a voltage divider and establishes the gate voltage owing to the plus minus 3 volt sources. So there are no such sources, there are no biasing resistor. So you see VG is essentially 0. So that means this is minus Vs, okay, or Vs can be written as minus VGSQ. So, and a gate to source voltage is determined from the assuming that the current source is the saturation current of the transistor. So using the same expression for the saturation current, VGS and IQ current relationship, you can write this as its IQ is 0.5. Just plug those values. Kn is 1 and VTN is 0.8 as given over here. Okay, you plug those values, and from the solving the quadratic, you see that VGSQ comes as 1.51 volts, which is gain minus Vs. Now the quiescent drain to source voltage VDSQ can be found out by applying the KVL at the output loop over here, and this is VDD 5 volts minus IDQRD. Okay, so VDD minus the current which is here, it's the same IQ, so I can write this as IQ or ID, it's the same thing. So VDD minus ID QRD is VD, so VD is your V0, right? VD is your V0. Then since this is VDS, so you have to take the difference with the source as well, which is evaluated as 1.51 volts. So VDD is known as 5 volts. Okay, IDQ is the same current as the current source at the source terminal. RD is 7 kilo ohms, and we have already determined VS as minus 1.51. This gives VDSQ as 3.01 volts. Okay. Now, so the transistor is therefore biased in the saturation region. Well, you can show this that your VGS minus VDN, which is the saturation point, which is the transition point, well, your VDS is greater than, so it is less than 3.01 volts. Okay, this is less than 3.01 volts. So so transistor is indeed biased in the saturation region. So our current and voltage relationship that we used was for the saturation current indeed. Okay. Now the small signal equivalent circuit is shown in figure 22. This is figure 22 over here, and assume that the source bypass capacitor acts as a short circuit, and okay. So over here you have this an AC source VI, which is connected across the gate resistor RG. And then we don't assume any other capacitance that like the gate capacitance or any MOSFET capacitances, and the input resistance of the MOSFET is high, so we have this VGS signal across RG, and for the NMOS device, the direction of the current is as such. That's given as transmittance gain multiplied by the input voltage VGS. Okay, so this is gate, the source is 0 because of the bypass capacitor. Okay, so the source, you see, due to the bypass capacitor, this becomes a short circuit over here. So basically your source, this is your gate, so the source is at ground potential. Then at the drain, this is also grounded, so RD comes with the ground, and your output voltage is given as minus GM VGS. Given the current direction, it's minus GM VGS RD, and since VGS is VI, there's no loading this time, so there's no loading at the input of the gate terminal. So VGS is VI. We have the complete signal voltage available at the gate terminal. The small signal voltage gain is thus, if you can take this VGS down in the denominator on the left hand side of the equation, so it becomes V0 over VIS minus GMRD, and just plug those values for the transmittance gain GM. GM can be found out from you have this the GM can be found out from the conduction parameter of the transistor, and the quiescent current as twice under root of Kn, which is unity, multiplied by 0.5. Okay, 0.5 is IQ. So basically So it becomes twice over under root 2, which is under root 2 again. This is about 1.41. Okay, so that's what we have over here. This is 1.41. Okay, so this is about under root 2, square root 2. So just plug this. RD 7 kilo ohms. Okay, and this gives the voltage gain as 9.9. So now you see this, if you compare this 9.9 with the voltage gain that we had without the bypass capacitor, is large. Okay, so it's important to include the bypass capacitor to have a full swing of the output voltage that we require, and with of course stability in the transmittance gain and the voltage gain. But if you don't have the bypass capacitor, you reduce the voltage gain. Although your Q point is stable, fine, but your voltage gain is reduced. So don't go for, you don't need to have a source resistor without the bypass capacitor. If you have a bypass capacitor, the source is at ground, okay, and all the input voltage is available across the resistor that appears at the gate terminal. Okay, over here this R1 parallel R2, but in this configuration there is no biasing resistances. Okay, in this configuration there is no biasing resistances, so there is only RG. So the voltage gain has improved. Now comparing the small signal voltage gain of 9.9 with example of the last example, which we calculated as 2.48, in example 4.5, we see that the magnitude of the gain increases when a source bypass capacitor is included. All of the Q point is stabilized. So this is an advantage of including the source capacitor. Okay, and a current source, which is also an NMOS device for biasing of the transistor. Okay, all right, that's all.